Hi everyone, this is Hangyu, Shao and Christine, and we are here to present our Pac-Man project. In this video, two methodologies to implement the agent will be introduced. Now let's begin from our first agent. The first method uses the side agent for both controller. One side agent is responsible for eating the opponent's top half food, and the other one is for the bottom half food. When the agent is a ghost, it will first head to the closest food it's interested directly. During this time, if it observes any invaders or the foods protected are less than the food protected at the last step, it will turn to the invader or the place of the missing food. If it observes any ghost, it will wait at the border of its territory that is the closest to the ghost. Actions are chosen based on the shortest path to the target object. When the agent is a Pac-Man, it will also head to the closest food first. If it observes that the food protected are less than the food protected at the last step, it will move to the place of the missing food. If it observes any protector, it will either try to find the capsule or go back home, depending on which one is more safer and closer. The number of foods carried by the agent is no more than 10, or else the agent will return the food no matter how close the other foods are. Actions made in this part are based on the breadth first search, with a value function for backward induction. The game theory is both our agent and the opponent's agent are always trying to maximize their value. The value of our agent state is the negative smallest maze distance from the agent to the border, or capsulate, or is infinite negative if it's captured by the opponent's ghost. The value of the opponent's agent state is the negative smallest maze distance from its agent to our Pac-Man. There is also a problem with our agent. When opponents goes close to the border, our agent will hover on the border back and forward, doing some useless movement. Method 2 use a variant of heuristic search, in which there should be a clear idea of goal states. However, in this Pac-Man contest, it is difficult to expand to the end of the games, due to the time limitation and the unknown enemy's behaviors. So a value function is used to evaluate all possible actions in a certain state. Higher value means its corresponding action has higher probability to succeed in the final. Now let us look through this method in detail. Suppose the current state is S0. My agent have to choose from available actions A1 and A2. So do my enemy. The search tree first expanded by each action. Then under each action, my enemy expand the tree further using their legal actions. Now we have a tree like this. The value of each leaf state node is calculated by state evaluation function. Specially, this function returns a weighted sum of several features in that state. These features including distance to the closest enemy, distance to closest food, the number of uneaten food, and so on. After that, these state values are backpropagation to their upper level action nodes. Value for an action node is average value of its all child state nodes. My agent will choose the action with maximum value. Notice the levels to expand in the tree can be changed by defining a depth parameter as long as the calculation time meets the limit. Based on their strategy, two agents are divided into one offensive agent and one defensive agent. Offensive agent always tries to eat more enemies' food and returns. The defensive agent defends its home when there are invaders. If there is not, it will invade and eat enemy's food. The main challenge experienced is that we tried to use search algorithm to find an exact best action in a certain state. However, There is no information about enemies' strategies, which partially decide success states. To handle this, we assume that each enemy has the same probability to choose its legal actions and return the expected value, which is an estimate of value of an action. Real-time computation is needed when playing games, so this method is limited in the tree depths. It can expand due to the 1 second constraint. Real-time computation is needed when playing games, so the method is limited in the tree depths it can expand due to the 1 second constraint. In another word, it may be short-sighted. Real-time computation is needed when playing games, so this method is limited in the tree depths. Real-time computation is needed when playing